Oh, that worked.
Science!
Find the right button. Someday the microphone won't work and it'll be silent Sunday. Or nobody will show up to sidewalk science and it'll be sidewalk silence. So Joanne and Phyllis and I and Deb Briggs and Liz was there. Were there yesterday for sidewalk science, and it was a lot of fun. A little slower than it has been a few other days, but we had some really nice conversations with folks about evolution and ancient critters on Earth. Our favorite critter is the Anomalocaris, which I believe, Mike, you started that fad.
Yeah.
And I get to talk about stellar nucleosynthesis, and I explained it to a 5-year-old who during most of the explanation I was talking about, stars, and it gets to be 15 million degrees in the heart of a star, and it makes elements and a sequence of elements up the periodic table, and the 5-year-old was. And then I had this, I should have brought it today, I had this little box with 3 meteorite fragments in it. And I showed him this box, and at the end of my story, I fairly consistently say, and then when a star makes iron, suddenly the energy of the star just turns off in a matter of minutes. A star that has been alive for millions or billions of years just turns off, and all the heat that was puffing up the outer layers of a star, that heat diminishes significantly, and the star just collapses, and it collapses in this titanic shockwave, just shatters the star. And I said, these little pieces of metal, rock, that we found here on Earth are the shattered heart of a dead star. Really? Yes, really. He looked up at his dad. Wow! Who knows? Maybe we changed that kid's life.
We're scared the heck out of them.
We're not scared the heck out of him.
Go stargazing again.
Yeah.
You fall on his head.
So we're having a lot of fun with sidewalk science. Usually we get, the age range is between 5 and 12, and then between 45 on up. So older teenagers, no way. No. And then adults, young adults, it's just too weird for them to talk to weird people. We're obviously trying to sell something, we're not. Anyway, if any of you see the postings on Meetup inviting you to come join us, please feel free to do so. We don't yet know what we're going to do this winter. In November and December, it's going to be too slow, too cold, too busy with other weekend activities, so we're not going to do it in November and December at least. But if anybody has any ideas about where we could do it during the winter, someplace where there are people walking by without lots of coats and scarves needing to be deployed. We were thinking inside of a mall. At the mall we approached, Joanne approached a mall and it said, well, how much will you pay us? I don't know. Anybody has any ideas? So today we had on the schedule a physician who's going to talk to us about plant-based diet and heart health. I made a mistake, which seems to be happening to me lately. I don't know what the cause of that is. But he had sent me an email 2 or 3 weeks ago saying he could not make this weekend, and I forgot about it. So I put him on the meetup and whatnot. He will be here in November. So instead, you get me. I put this together yesterday afternoon after Sidewalk Science. So my intent is to pursue kind of a conversation arc that Mike suggested that we engage in, which is origin stories. Now, for many people, it's an origin myth, but scientists have been able to take some of the mythological ideas and either show that they are incompatible with physical evidence and or replace myths with science. And we'll talk a little bit about that today. Part of my intention is I want to take this as slowly and thoroughly as you all wish. So if you allow me to get through all my slides today, that's great. If not, I live in the area, I'll be back, so we can continue at some later point. So don't be afraid to ask questions, raise your hands, interject, tell me I'm full of it, whatever your interjection may be, so that we can get through this material, hopefully in a substantive and complete way. All right. I want to talk about the origins of the earth. When I was a kid, I wanted to be a preacher. I was sort of a standout in Sunday school. I memorized a lot of Bible stories, and I was thoughtful about them and had all kinds of philosophies and whatnot. So I was certain that I was going to grow up and be a preacher because everybody told me that was the way it was going to be. I fell in love with science and decided that that provided a much more cogent, cohesive, and elegant explanation for the way the world works. And so I started reading other books to get my answers about the big questions. Where do we come from? Why are we here? How did we get to be the way we are, etc. But throughout, at least the United States, there is a pervasive creation myth that goes something like, in the beginning, God created the heavens and the earth was without form and void, and darkness was upon the face of the earth, face of the deep. And the Spirit of God moved upon the face of the waters. And God said, let there be light, and there was light. Notice how light comes after water. And God saw the light, and it was good. And God divided the light from the darkness, and God called the light day, and the darkness he called night. So whoever wrote that, if they indeed had a hotline to somebody that knew how the universe got started, their dictation was significantly in error. There are many mistakes in this account. And yet, for at least 2,000 years of human history, probably more, something like this has been the basis of our understanding of how everything came to be. Let's talk about what we have learned instead. Oh, happy Halloween, everybody, by the way. Yeah. I kind of see the jack-o'-lantern in that. Yeah. That's supposed to be an artist, well, it is an artist rendition of the baby Earth. And the baby Earth was first conglomerated out of cosmic particles and meteors and dust and gases and whatnot during an era known as the Hadean. And it was a hellish time, right? Meteorites and whatnot bombarded the Earth. So here is a schematic diagram that somebody has come up with in one of the books I have. This is a diagram of different creation myths, right? You can read this. Do you know how to use a flow chart? The little diamond boxes up here are where you make decisions. Is there a beginning? If yes, then go down this way. Was there perhaps not a beginning? No. And this is sort of a schematic representation of the options for creation myths. The Hindus, for example, have the idea of a cyclic creation. The universe is generated, it persists for some time, and then it's destroyed and gets regenerated. And that's consistent with some cosmological ideas that, because of something called dark energy, are no longer still in vogue. But there is a cosmological scientific idea that the universe, the Big Bang happens, the universe expands, and it slows down and slows down and slows down, and then there's this thing called a big crunch, and the universe collapses down again, and the whole cycle just repeats ad infinitum. So there are some aspects of some myths that are consistent with scientific explanation. Obviously, the universe, all the stars we see, the Earth itself, had to come from somewhere, from something. So anytime we attempt to answer those sorts of questions, you're going to be asking the same sorts of questions, and maybe even some of the answers that you propose, like whether it's cyclical, or whether it's a one-time event, or whether the universe or the Earth has been around literally forever, infinitely far into the past. Those are your three options, right? It has a starting point, it's a cycle, or it's always been here. And people like the ancient Greeks thought that it had always been here, some Greek myths. So now, science tells us that the universe, the Big Bang, commenced from something that I call the cosmological nugget, or the primordial nugget. Nobody knows for sure what it looks like, so this is my imagining. The cosmological nugget, Brian Greene, in his book, not The Fabric of the Universe, but the other one. The what? The Elegant Universe, thank you. In The Elegant Universe, Brian Greene says that the cosmological nugget was about 10 to the minus 28 meters in size. So that's much, much, much smaller than a pinhead. For comparison, a proton is about 10 to the minus 15 meters. So this is about, a billion times smaller than a proton was the cosmological nugget. Now, the thing about the cosmological nugget is that scientists can use evidence from particle accelerators. It can use evidence gleaned from astronomical observations about the way things in the universe are moving relative to one another. Certainly it can use the cosmic microwave background, which some of you may be familiar with. I'll talk more about in a minute. They can use all kinds of signals obtained from natural processes to figure out an amazing story about the way the universe came to be. And all of the best science we have can take us back to the point when the universe was about 10 to the minus 46 seconds since the commencement of the Big Bang. Now, what happened prior to that, prior to the banging, remains a complete mystery. The cosmological nugget could have sat, metaphorically speaking, perched on a precipice of action for an arbitrary amount of time prior to that. It's a common error of popular television shows and other sources to say that the universe started from a singularity, which is a point of infinite density and infinitesimal size. Well, 10 to the minus 28 is pretty infinitesimal, but it's not zero. It's not a singularity, right? Well, our science and the evidence consistent with the observations we've made about the natural universe tell us that the universe could not, it just could not have started as a singularity. If it had started out as a singularity, there would be ramifications of that we would see evidenced in things like the cosmic microwave background radiation. So, for those of you who like to talk about cosmology with your friends, if your friends stipulate that the universe started out as an infinitely dense and tiny singularity, maybe now you know enough to tell them that that's wrong, which is one of the most fun things that can come out of a person's mouth, I think. Second only to, I don't know, which is a very common statement that scientists make. So anyway, this cosmological nugget, I told you how big it was, I told you when it existed. How heavy was it? You know, you look at the universe and it's got something like 10 to 80 particles, 10 to 80 protons-ish, right? And that's really heavy. Quintillions and septillions and numbers that don't even have names about how massive the universe was. The cosmological nugget, which became everything we see and measure, every bit of matter that we are made out of, weighed 20 pounds. According to what Brian Greene says. And he would know his stuff. He's a professional theoretical physicist, very highly regarded. So, how did the universe get to have Well, obviously more than 20 pounds, right? When it started off so small and so light. Well, there was this idea of something called cosmic inflation. So this far outstrips anything you've heard about in economic inflation. In something like 10 to the minus 26 seconds, the universe expanded by about 26 orders of magnitude. It went from a size smaller than a proton to a size somewhere between a basketball and Jupiter. They're not really sure, right? It went from a magnific little point to something maybe the size of something visible in a tiny fraction of a second. And there was a field, I don't want to get into this too deeply, I can, like I said, I'll take as much time as we need. Every force of nature, every particle in nature, whether it's an electron or a neutrino or a photon, every particle in nature is associated with a field that permeates all of nature. And one of those fields that was relevant in the early universe was the inflationary field, and this was a field of potential energy. Well, as the inflation process took hold and expanded space itself, the energy, the potential energy of that inflationary field was dumped into creating things like photons and electrons and protons and neutrons and bonbon. No, there's no bonbons. Perhaps protons, maybe. So, during the brief period of cosmic inflation, the universe became almost perfectly uniform. Right? Think of starting with a crinkled balloon, just a deflated and crinkled balloon, and if you blow it up, it becomes smooth. All those crinkles go away, right? Well, that's one of the effects of cosmic inflation, was that any inhomogeneities in the initial cosmological nugget, the little bumps and irregular shapes and whatnot, got smoothed out. And we see an almost perfectly smooth cosmos. And that smoothness is represented by the fact that anywhere you look in the sky, you see the same leftover radiation from a time when the universe was about 380,000 years old. It's light left over from the Big Bang, and that light, when it was emitted, the universe was smaller, and now the universe is larger, so we see that light from a different frame of reference. And from the frame of reference today, we see that light as microwave radiation, whereas when it was emitted, it would have been in the deep red, just on the edge between infrared and visible red light. So there are all kinds of implications of an inflationary universe, of a moment of inflation, having to do with the smoothness of space and the existence of the cosmic microwave background radiation. And we see evidence consistent with those physical processes whenever we look at the distribution and motion of galaxies and the details of the cosmic microwave background radiation. So, before I move on, anybody have any questions? Yes?
Mike, what caused the inflation?
Yeah, I don't know the answer to that. There may be physicists who do. My sort of back of the envelope sleeve, wearing on my sleeve explanation is that the potential to interact with an inflationary field is always present in matter, but different processes in nature literally freeze out of the potential of the universe as the universe cools. For example, when the universe was only fractions of a second old, the electromagnetic force of nature and something called the weak nuclear force were provably the same thing. Instead of being two distinct forces of nature, they were the same force of nature, until the universe cooled off a little bit. And prior to that, the strong nuclear force was also unified with those other two. So as the universe expanded and cooled, these different effects, these different forces of nature became distinct mechanisms. Well, the inflationary field was such that it operated on the state of the universe long, long ago, and that state is no longer available to us. No particle accelerator can even approach the kinds of energies and temperatures at which the inflationary field and the effects of the field become relevant. But as for how it grabbed onto space-time and caused it to spread, I don't know the details of that. Yes?
Where did all the matter come from when you start? Something only 20 pounds.
Yeah, so the inflationary field was potential energy, which is essentially negative energy, and that energy was balanced by the creation of positive energy in the form of light and matter, such that the total energy content of the universe, perhaps accepting that 20 pounds, I'm not sure about that, but in the main, the total energy content of the universe is exactly zero, because the negative potential energy of the gravitational attraction and initially the negative potential energy of the inflationary field was perfectly balanced. As the field operated on the baby universe, that energy was perfectly balanced by the generation of light and matter particles. So that it's essentially the energy of the inflationary field that got, as it operated on that initial little nugget, got instantiated as other matter and energy particles.
So it came from energy?
Yes. Yeah, the E equals mc squared, or m is equal to E divided by c squared. You can just rearrange that. Any other questions?
Is that what you're saying, kind of based on Lawrence Krauss's, how the universe came from nothing? Is it something different that he's saying?
It is certainly a part of his hypothesis. So the idea that the universe has a total energy of zero is pretty well established among cosmologists. Lawrence Krauss goes a step further and say, well, where did the cosmological nugget come from, right? That initial little pinprick of matter and energy and potential, right, including the inflationary field. Where did that come from? And his argument is that it is nothing except a quantum perturbation of some pre-existing space-time multidimensional manifold, right? So his speculation takes the total energy of zero for the universe and adds on to that, yes, but how did the nugget come into being? So it goes a little bit further than that. And some physicists, most notably, I think, Frank Wilczek, I saw a YouTube video, a debate between them. Frank Wilczek won the Nobel Prize for physics a few years ago. And Lawrence Krauss was talking to him about this idea of a universe from nothing. And Frank Wilczek, and other philosophers, by the way, have pointed out a philosophical problem with Lawrence's argument, and that is it presumes or presupposes that the laws of nature that we know about today were relevant to the universe, or the metaverse, if you will, that existed prior to the generation of the cosmological nugget. And that's quite a leap of faith, right? There's no evidence of that, and we're not even sure that there's any way to get any evidence of that. But it's an interesting conjecture. Any other questions? Yeah.
Sorry, Scott, I've just been trying to drag this name out of my mind, but I can't do it, so maybe you can. There's a person who's theorizing changes in the law of physics. I can't think of the person's name, but that might be evidence for that argument that actually the laws of physics aren't constant. Do you know who I'm talking about?
Well, that's a pretty general hypothesis. I know of lots of people who think that the laws of physics are constant, but they don't tend to be physicists.
No, this is a physicist.
Okay.
I'll have to look it up again. Sorry.
Well,
But
there's
do you know of any physicists who argue that the laws of physics aren't constant in the larger history?
Yes, in specific instances dealing with specific laws, I know of a couple of instances. There's a fellow who came up with the idea of tired light, for example, that light loses energy as it travels, because analogously to the way your car is climbing uphill. It takes energy to make it continue moving. And that idea of tired light, which could plausibly, if it were true, could plausibly explain things like cosmological redshifts and whatnot. There are other cosmological and mathematical arguments that show that that just cannot be true. So that's been pretty thoroughly debunked. There's another idea that the gravitational constant, which appears in both Newton's laws and Einstein's general relativity description of gravity, that the gravitational constant is not, in fact, constant over time. And there's not a lot of evidence for that either, because it would have implications on the way that stars that are very, very far away, which means we're seeing them as they were billions of years ago when the universe was much younger. If the gravitational constant were different, or if the electromagnetic constant were different, the stars that we see that are very far away would behave differently than stars that we see that are closer to us. Now, stars that are very far away we cannot see as distinct stars, but we can see the aggregate light of distant galaxies to figure out kind of how the stars within them are operating. So both the change in the speed of light and the change in the gravitational constant are not very well accepted ideas. There's a little bit more wiggle room in the gravitational constant argument. One thing that certainly is changing is a constant that's involved in some of the laws of nature called the Hubble constant. And when Edwin Hubble, back in the early 1900s, looked at the night sky and thought about the relationship of the motions of distant galaxies to what Einstein's equations said about the way gravitationally interacting things would work, he deduced that the universe is expanding. And at the time, and up until the 1980s, it was assumed that that rate of expansion was constant, hence the Hubble constant. Well, in the late 80s and the 90s, it was discovered that the rate of expansion of the universe is actually increasing. And so the Hubble constant is a Hubble variable, right? So those are the instances I know of where the laws of physics might be changing, those very specific instances. I don't know of anything more generic.
I mean, to talk specifically about people as physicists saying that something hadn't changed, something was different in physics, you could talk about the cold fusion experiments and the development of people saying, we've come up in Utah, right, with cold fusion, and that was going to change the energy needs of the world and so on.
Oh, absolutely. Yeah, so you know, physicists make remarkable discoveries all the time, and some physicists who think they've made remarkable discoveries have not done so, right? So cold fusion is an example of that, and there's a whole scandal involving the university and the way that it was handled and whatnot. But an even better, more recent example, in my opinion, is some Italian physicists who measured the speed of a neutrino and decided that it moved faster than light. Well, this is literally universe changing, if it's true. And so they published their data. They said, here's how we calculated the results of this data, and according to our calculations, this means that the neutrinos move faster than light. That would literally turn physics and cosmology on its ear. It is previously an inconceivable notion, because in a very real sense, the speed of light is an infinite speed. Insofar as if I want to get from here to some distant place, if I move at the speed of light, I get there in 0 time. Well, that's the same as moving at an infinite speed, right? You get that, right? So the speed of light is nature's infinite speed. The problem is when you start considering the speed of something moving at the speed of light and the way time changes for something moving at the speed of light compared to something that's moving slower, right? That's where relativity comes in. So anyway, a neutrino that moves faster than light would change fundamental physics and prove Einstein wrong, right? Big deal. Well, they did some analysis on the experiment, and they found out that the data that they had was due to a loose cable. So it is true, that just like finding that the Hubble constant is not a constant, but the Hubble constant is variable. There are occasionally instances in modern physics, certainly many in early physics, when things that were assumed to be true are found to be in error. So there are revolutionary ideas occasionally. Carl Sagan, my hero, in many respects, said that he popularized, he didn't come up with this idea, he popularized the idea that extraordinary claims require extraordinary evidence. Right? Any other questions before I move on? Right. So this is the history of the universe. The Big Bang commenced somewhere here. Again, how long the cosmological nugget existed prior to that, nobody knows. The Big Bang commenced about 380,000 years after that, 375,000 years. The chemical composition of the universe and the ionization of the atoms comprising all the gas in space had reached a point where light could travel through space. And this is where we see the cosmic microwave background radiation. And then somewhere in here, the first stars formed, somewhere between 375,000 and 400 million years, the first stars formed, and then galaxies and clusters of galaxies and whatnot. And about here, about 9.5 billion years ago, the Earth was generated. So there was a lot of history in the universe prior to the generation or formation of the Earth. And then since then, the universe has continued on its merry way. So for the past 4.7 billion years, since the Earth formed, the universe has continued. And it's been only, I'm sorry, was there a question? It's been only recently that the increasing rate of the expansion of the universe has become relevant. That's why this is kind of a little saddle shape here towards the end. And then the history of humanity is so thin in this graph that you can't even see it unless it's oblique.
What are the dark ages?
The Dark Ages, there weren't any stars there. So that was prior to the formation of the first stars. Light left over from the Big Bang could travel through space, but stars had not yet formed. There's also age of ionization, an age of reionization, where the universe was so hot that, or the first stars, essentially the first stars in the universe reionized all the gas that was the hydrogen gas that was the main component of the matter of the universe. So the first stars were made only of hydrogen and tiny little bits of lithium, which is very important if you're a stellar astrophysicist. But in any case, the first stars essentially reionized the gas of the universe and made it such that it absorbed light more readily. So the universe turned dark again.
So roughly for the first 10 billion years, the universe was not accelerating in its expansion, but was constant.
Yeah, yes. It was expanding
Constant.
constantly, but the rate of expansion, I mean, the rate of change of the Hubble constant depends somewhat on the size of the universe. So as the universe size increases, the rate of expansion increases. It's the rate of one thing is related to the size of another thing, kind of a differential equation thing. But in the earlier universe, the size of the universe was small enough that the acceleration of the expansion rate was trivial, unmeasurable. Any other questions about the universe? You got it, all right, good. All right, this is where we live. Like I said, I made this yesterday afternoon. I got into my spaceship and I went out and took this picture of the Milky Way from M13, a globular cluster that orbits the Milky Way. No, this is a different galaxy. But it's a galaxy that looks probably a lot like the Milky Way. The Milky Way is what's called a barred, not barred as in a singer, but a bard as in a bar of iron, right? A barred spiral galaxy. So if you look closely towards the center, the bright region of this galaxy, you can see a bar, a bright band of stars, instead of one of the sweeping arms of stars. So our Milky Way galaxy, from the outside, would look something like this. Now, if you, I'm going to ask for forgiveness after I say this, not before it. So, if you hold to the idea that a creator generated the universe for the pleasure and potentiality of human beings, then you might say, well, this is it. This is how it came to be. This is our galaxy. This provides a nice place for stars to come and go and generate all the elements that are necessary for living things, which I can talk about in a minute. But this is all the universe you would need. This is perhaps even more than you need in order to provide a habitable environment for the formation of the Earth and the Sun, even according to the laws of physics. Right? This is all you need. Right? Oh, this is what our galaxy looks like from the inside. Those of you who haven't seen it, it's the Milky Way, right? You see splashed across the sky. But if all you need is one galaxy, or even a fraction of one galaxy, then what's up with all of these things? Every little dot, every splat, every piece of light you see in this image is another galaxy. Right? There are something like 1 or 2 trillion galaxies in the observable universe. Right? Talk about overkill. If the whole point is to generate an Earth with you and me, then, well, A for effort. Now this leads to all kinds of natural speculations about, are we likely to be alone in the universe? Are there likely to be other intelligent beings? I talked about that last year when I discussed the Drake equation and sort of a mathematical framework for putting bounds on the probability of intelligent life being elsewhere in the universe. But it's a mighty big universe. Each of those 2 trillion galaxies is a host to 100 billion stars, give or take. Right? Gigantic universe with all kinds of potential. And just because I'm taking as much time as I want, I can continue this later, I will tell you that some astrophysicists think it's perfectly plausible that there's actually an infinite number of galaxies that were generated during our Big Bang.
Whatever that number is.
I'm sorry? I didn't hear you.
Infinity?
Yes.
Infinity?
Yes.
Big number, not infinity.
No, they think that there is an infinite. There is no reason to suppose that there is any limit to the amount of energy in space that could have been entailed in the formation of the universe. So some cosmologists and astrophysicists think that because there is no a priori reason for assuming a limit, there is literally no limit. Now, the way I explained this previously is to imagine a sheet of paper, right? And you can imagine that a sheet of paper, according to high school geometry, extends infinitely far. Well, there are other theories that say that our Big Bang was not the only Big Bang, that Big Bangs are things that happen all the time, right? Instead of Lawrence Krauss saying that our Big Bang was quantum perturbation, maybe Big Bangs are just a property of what happens of a kind of metaverse or motherverse, as I've called it. And Big Bangs are happening all the time. Well, if each Big Bang creates an infinite sheet of paper, you can stack pieces of paper up one on top of each other, and you can have arbitrarily many, even perhaps an infinite number. So it's a way to get around the problem of the universe having a beginning. Maybe the universe is infinite. in terms of it's always been here, it's just a property of the way things are. And if that's true, there could be any number, and literally infinite number of universes, and each universe could have generated an infinite amount of matter. The problem is that it's only been 13.8 billion years since the Big Bang. So anything we can perceive about what inhabits our universe, all the stuff in the universe, all that we can ever see or know for certain is about material that has emitted light at the most from 13.8 billion years ago. So as the universe has expanded, we have what's called a cosmological horizon. Now, imagine that from our point of view, no matter which direction we look, the universe looks like it's 13.8 billion years extending, light years, extending in the other direction. Well, if the Earth happened to be 13.8 billion years over to my left, you're right, then does that mean that if I'm right there, if the Earth happened to be right there at the edge of what we call our visible universe, and we looked off to that side, would we see nothing? Would we see a black sky? Right? Plausibly, not probably, not certainly, but plausibly the answer to that question is no, we wouldn't see a black sky. We'd see 13.8 billion years in that direction. Well, what if I go to the end of that 13.8 billion years and look out at the sky? Will I see darkness? Will I be at the edge of the universe? No. Right? So there's a couple of problems with that metaphor that I won't get into unless somebody asks me a question about it specifically. But that's the kind of argument that cosmologists have used to justify the fact that there's no a priori reason to assume that the amount of space and energy that got generated in our little bubble universe during the Big Bang has any finite limit.
So basically what you're saying then is that our knowable universe is limited to 13.8 billion years.
Yes. Yeah. There's a
Not the potential entire universe, but the knowable universe.
right, and that gets into discussions of the multiverse. The kind of multiverse that I'm describing, I've talked about two. I've hinted at two. The first is called the eternal inflation multiverse, right, where inflationary Big Bangs are happening all the time. And the second kind of multiverse that I just described, where there is no finite cosmological horizon, is called the statistical multiverse. And I talk about that in one of my books that I'm getting ready to publish. So there are other kinds of multiverses too that aren't relevant to today's subject. Yeah.
Your slides had some implication that there was some kind of directionality from the Big Bang. Is that actually, is there any evidence for that, or was that just the
Great question.
visual representation of?
Right. Did everybody hear the question?
Mm-hmm.
Okay. So the idea is that picture I showed, the funnel, the universe going off, looked like the universe went off in a particular direction. Well, that's a cross-section of a volume that is essentially a sphere. And that was a direction in time. So time moved from the Big Bang to the present day. But the universe, so again, something I talk about in my book is a common misrepresentation of the Big Bang is that there's some cameraman and a special effects team positioned somewhere 40,000 light years off to the left of the Big Bang. And there they are filming, and they film the Big Bang, and there's this giant fireworks explosion. And this, equations and galaxies rush at you from the Big Bang. Well, that's just not the way it works, right? The Big Bang happened everywhere at the same time. There was no point that had a firework, right? The universe was hot everywhere. Matter was generated, electrons and protons were generated from the inflationary field everywhere. It didn't happen at a point. And over time, the volume of the universe has expanded according to what Hubble discovered and Einstein's equations predicted. Other questions? Yes?
Wouldn't you know when you've reached the end of the universe because there's a restaurant there?
Yes. Yes.
It's a 7-Eleven.
Yes. Right.
So, I got a question for you.
Yeah.
if I may. We hear that the universe is expanding, but it sounds like, from what I've heard, that it seems to be going outward from some central point. But what you're saying now, if I understood you correctly, is that's not true.
You understand me correctly.
Okay.
Yes. So the analogy I used several years ago when I talked about the Big Bang, I brought in a giant balloon, and I blew up a balloon. And if you're an ant standing on a balloon, or a human being standing on a curved earth, a spherical earth, you can plausibly say that you are at the center of the world, because you look out and you see a horizon all around you. Well, I must be at the center, because no matter where I look in the same distance away, I see a horizon. Therefore, I must be in the center. Well, if you move halfway around the sphere, you still think that you're in the center, right? It has to do with the difficulty we have about thinking about a four-dimensional space, or four-dimensional space-time. So there is no center. Now, you can say, oh, yes, but a balloon has a center because I can cut through it, right? Well, that gets into necessitating thinking about the way the universe exists as a four-dimensional entity, right? But from our perspective as three-dimensional beings living in a three-dimensional space, there is no center of the universe. Every place in the universe experienced the Big Bang. Every place in the universe, no matter where you are, the universe looks like it's rushing away. Now, after Hubble came out with this amazing discovery that every galaxy is rushing away from the Earth, there wasn't a single scientist who said, oh, well, the Earth must smell bad, right? The whole cosmos is rushing away from Earth. Obviously, we are the center of creation, and the rest of us are trying to get the hell out of here, right? Not a single scientist said that, even though that's what it looked like, just like it looks like the sun goes around the Earth, right? By then, the theory describing the geometry of the universe and the properties of the universe were so well accepted and deeply understood and integrated into our models of the universe that nobody presumed that the universe was trying to run away from Earth. We understood this whole ant on a balloon thing so that every place would look like the center. A common analogy is raisin bread. You take dough and you put raisins in it and you put it in the oven and the dough expands. And the raisins, each raisin, no matter where it is in the bread, assuming you have an infinite loaf of bread, each raisin sees every other raisin moving away from it, no matter where that raisin is located. Now, the common question, one of them that I address in my book, is, well, why didn't the raisins expand? Right? If space is expanding, then why aren't galaxies and atoms expanding? Right? That's a reasonable question. Well, galaxies are held together by the force of gravity. Atoms are held together by electromagnetic forces. Nuclei of atoms are held together by the strong nuclear force. These forces are vastly more powerful than the very slight tendency of the universe to, relatively speaking, the slight tendency of the universe to expand. So anything that is clumped together because of electromagnetic or gravitational forces resists the tendency of the universe to expand. It's the space between things that gets bigger, it's not the things themselves. Okay? Any other discussions about that?
Space between the sun and the earth is getting bigger, but not big enough to worry about.
The answer to that is a little nuanced. So the question is the space between the Earth and the Sun therefore getting bigger? When I said the space between things gets bigger. No, because the gravitational forces between the Sun and the Earth are far overpowering the tendency of space to expand. So, you know, it's not just the gravitational forces holding the Earth as a sphere, but it's the gravitational forces that hold distant stars together in a galaxy, or that hold galaxies together as clusters of galaxies or groups of galaxies. So the force of gravity, and certainly the force of electromagnetism, is perfectly sufficient to create local clustering of matter that ignores the expansion of space. And the reason it's a little nuanced is because if it's true that dark energy will continue to increase infinitely as the universe ages, then something like 10 to the 80 years from now, or some astronomical number like that, the influence of dark energy will be so great, the amount of dark energy per cubic centimeter will become so great that it does overcome gravity and rips apart galaxies and stars and planets, and eventually it becomes so strong that it'll rip apart atoms. That's called the Big Rip. It's kind of a bleak future, but we've got a long ways to wait for it.
In the interim, can we think of it more in terms of intergalactic space is what is?
Yes, intergalactic space is tending to expand.
Yeah.
Rich?
Yeah, continuing that same line of thought. So the distance between bodies within our solar system is not increasing. But
Due to the
between-
expansion of the universe, right?
Okay, but between the solar systems within our galaxy, those are increasing the distance between them?
Yeah, as Jamie said, this effect of the cosmic expansion of the universe is really only visible in between galaxies. So the stars within a galaxy have our star compared to Alpha and Proxima Centauri, which has a very tiny gravitational effect. So tiny we can't devise any experiment to measure the gravitational influence of Proxima Centauri on our sun and our planet. That's still bigger than big enough to overcome the tendency of the universe to expand. So a galaxy will not expand and blow up as space expands. It's only the spaces that, relatively speaking, perfectly empty space in between galaxies. Yeah.
So Scott, why is it expanding faster now?
And how are you measuring
What was the
that?
question?
Why is it expanding faster now? The first person to answer that question correctly gets a trip to Stockholm.
Oh,
This is just what the evidence
Work on
tells. I'm sorry?
so you can work on that.
Yeah, right. Yeah, I'm never going to work on that. My math skills aren't up to snuff. But, yeah, this is just what the observational evidence of the way the universe behaves has led to this conclusion, this inescapable conclusion that the rate of expansion is increasing. Nobody knows why. Nobody knows the source of this, what's called dark energy, or another name for it is the cosmological constant.
So is the creation of dark energy somehow causing the expansion?
I don't, there's a presumption in your question that it's the creation of dark energy. The
Formation.
Yeah, or the formation of dark energy. Dark energy is a property of empty space that is tied to, the amount of dark energy is proportional to the volume of empty space, and normal Hubble-based expansion of space is creating more and more space in between gravitationally bound things all the time. So the amount of dark energy is increasing over time. So the nature of dark energy,
So it's a relationship but not causal.
right,
Okay.
yeah,
Scott, do you
yes.
think there's some form of life out there? Some form of life?
Absolutely. Is there a form of life out in the universe? I'm as convinced as you can be without evidence. I think it is an incredibly plausible conjecture that life exists out in the universe. Now, it becomes less plausible if you start speculating about whether intelligent life exists in the universe, because the chain of events that led to life existed on our planet for something like 3 billion years before life evolved the capability to have cells glom together to make complex organisms, right? So was that a fluke? Was there really just one universal common multi-cell ancestor for every other multi-cell creature on Earth? And was that a fluke, a statistical fluke that might not have happened ever, right? So thinking about life, bacterial life, viruses predating bacteria, whatnot, I think it's damn near a certainty. But whether there is complex life, much less intelligent life, I have no clue. Other questions here?
Wasn't there an idea that the quantum, where particles pop into existence and annihilate, and it's that effect that is expanding space, which is causing which is the dark energy?
Yeah, there's There's a big problem at the heart of something called quantum electrodynamics, which is our best description of the way the electric force works. And the big problem is that when you calculate the energy of empty space, according to quantum electrodynamics, when you take everything into account, every possible way that a one charged particle can interact with another charged particle, you end up with a value for the background energy density of empty space, right? And think of it analogously to the fact that we're under pressure right now in our atmosphere, but you don't feel pressure. Nothing prevents you from lifting your arms, right? Because the pressure everywhere is constant, right? You don't have to lift the atmosphere to raise your arms. Well, there's a similar way to calculate the energy of empty space according to quantum electrodynamics that still allows electrons and protons to form atoms and all this. But when that calculation is done, they come up with, Joanne's going to cringe, infinity. Right? Something must be wrong with the equation, right? So they can subtract off almost all of that infinity. Oh my God, it gets weird, right? They can subtract off most of the infinity and what they're left with is sufficient to explain electrical forces. But whether or not the quantum electrodynamic background of empty space, and there's more than just electricity, there's force between quarks and the other forces of nature. Whether or not the background energy density of those force fields, those force potentials, is sufficient to explain dark energy is an open question. And I don't think anybody knows whether that is the source of dark energy or not. But it is a speculation. Other questions? Okay. So how does this compare to that Genesis thing?
It was interesting that you had the Dark Age up there, and it kind of brought me back to part of what I heard when I first walked in. I was about 5 minutes late, where you were talking about the separation of water from earth and light from darkness. Well, there's a period there where there was no light, and all of a sudden he said, "Let there be light."
Yeah.
And guess what? So, curious.
Yeah, one of the tendencies people have had over the years, as science has discovered more and more about the history and fate of the universe according to the evidence, is people have tried to fit that with accounts from various religious traditions. And I think those attempts have met with fairly limited success. You have to read a lot in between the lines to make them fit.
You can count all those other galaxies as throwaway practice ones.
Yeah, right. Yeah, you have to do something like
You have to give up the perfection of God.
Right, you have to assume that 2 trillion galaxies plus one, all the others were just practice, you know, and maybe they were in error. Well, if they were in error, well, see. Okay, this is a region of space called the Witch Head Nebula. You can probably see why. It's Halloween, so I had to use this picture near Halloween. So this is a region of gas and dust in space. It's called a reflection nebula. This nebula is lighted by the blue light of a star named Rigel in the constellation Orion. And this is the reflected light of that nebula. And then here, speaking of Orion, this is the constellation Orion. You see the belt and the sword here? This is a very long exposure picture of the constellation Orion. Well, what's all this red stuff? You don't see that when you look up in the sky. Well, this is very tenuous gas that glows very dimly, and you need a long exposure photograph to be able to see this. But the constellation Orion is awash in gas and dust. So much gas and dust that we could form something like, I wrote the number down here because doing math in my head has not been one of my skills, 200,000 times the mass of the sun in all these clouds of gas and dust. 200,000 suns. Well, the most famous portion of this is the Orion Nebula down here. This ends up being a little fuzzy picture of it, but you can really zoom in on the Orion Nebula, and it's one of the most beautiful things in the sky. I will tell those of you who have a telescope, though, if you look at the Orion Nebula through a telescope, even a large telescope, it looks like a fuzzy green spot. because your eye isn't particularly sensitive to the really dim red light. You need a long exposure photograph. All right, stars age, and they eventually blow up. And this is the thing that made the kid go, wow, this is stellar nucleosynthesis. But unfortunately, I am out of time, which is fine. I'll be back. And we'll continue the story about the way stars generate all the matter that became Earth and the way the Earth got formed at a later date. Thank you very much.